looks like you have to hit. Oh, there it goes. It goes. All right. And it's in presenter mode and everything. So, so the first speaker today will be Angela Desjardins from Montana State University, talking about the Nationwide Eclipse Ballooning Project. And if you need it, there's a laser pointer right there.
Wonderful.
Okay.
Thank you. Hello, everybody. Super happy to be here and to be talking with all of you. And I just have to start with a little bit of a disclaimer that we're not really a citizen science project by some version of the definition, because participating in this project is actually really quite expensive and so not really available to the average citizen. But we are like citizen science projects, and then we have a huge number of people, of teams participating and people on those teams. So just with that disclaimer, I wanted to go ahead and get started. This title slide actually means a lot to me, but in 8 minutes I can't do it justice, so I'll just move on. But all of these groups are represented in this work. So I want to talk a little bit about the project in general, what it is, student impacts, and then I'm going to very quickly go over atmospheric science results and engineering results. Each of these could be an hour-long talk, so I'll be just whipping through as fast as I can. But the main purpose of this project is really has to do with this quote. This means a lot to me in my day job as director of the Montana Space Grant and NASA EPSCoR, but it's also very important in this project. And we're really about giving students hands-on opportunities to actually help them understand their chosen careers. So we're primarily in the higher education realm with primarily undergraduate students, but a lot of those people don't actually have the opportunity to get a feel of what it feels like to be a mechanical engineer, electrical engineer, you know, a physicist, you know, something like that, unless they get some hands-on work. And there's just not enough of those opportunities to go around. So really, you know, the core of this project in a lot of ways is to give opportunities to students who wouldn't have them otherwise. So just a really quick background, you know, ever since the whole Chinese balloon incident, people understand what we mean by high altitude ballooning better than they did before. So explaining this is maybe a little bit easier than it was before that. But the really great thing about doing high altitude ballooning, it's often called or stratospheric ballooning or academic ballooning, things like lots of different names, is that it's a space-like environment for a much lower cost than it would be on a rocket. It's also really wonderful because it's very multidisciplinary. You need students from all different kinds of, or people from all different kinds of backgrounds to be able to do that. And it's really like a little mini mission. So that's really great. Flights on tide balloons, which again is a whole other talk, go up to about 100,000 feet, expand because of the low pressure, pop and come down on a parachute. So that's the typical architecture. In this particular project, so the Nationwide Eclipse Ballooning Project has been going for about 10 years with a variety of different eclipses. In this particular instance, for the annular eclipse and the total eclipse, we have two different tracks. Atmospheric science, which we had 19 teams flying radiosondes, which if you don't know, they're the little weather sensors that the National Weather Service uses at least twice a day, every day from the 92 different weather stations around the country. And that basically is what gives us our weather predictions. They measure temperature, pressure via GPS, just GPS location, humidity, and wind direction, wind speed. So atmospheric science flew those once an hour, every hour, 24 hours before the eclipse and 6 hours after. And if you do the math with our 19 teams, that's about 600 balloons for each eclipse. So really quite significant. And with data every second, you can start to get an idea of the kinds of data that we're dealing with. And then the other track is the engineering track. We had 34 teams on that track. And those teams fly more payloads that they get to build themselves and flew 1 or 2 or sometimes 3 balloons. So in that instance, it's more about what you put on the balloon and all of the work going into those different payloads and just doing that like a few times. So what are our science goals? Our primary science objective is to understand how the atmosphere responds to the cold, dark shadow of the eclipse. One of the main things we were looking at is gravity waves generated by the eclipse, which is not to be confused with gravitational waves, right? We are not measuring minuscule little waves from interacting black holes. We're many magnitudes of scale, are many magnitudes larger than that. So gravity waves are waves that happen in the atmosphere all the time. They're kind of like ripples in a pond. So if you've ever seen clouds like this, those are clouds sitting in the troughs of gravity waves. They're generated from temperature changes like day and night, and also things like mountain ranges, and when you have like strong jet streams and things like that. So they happen all the time, and we're trying to understand, does the cold, dark shadow of the eclipse generate these gravity waves different from, the gravity waves that you get from like day and night changes? We first saw evidence for eclipse-driven gravity waves with the July 2nd, 2019 eclipse, where we sent a team from Montana down to Chile and saw the first ever stratospheric gravity waves, evidence for that, and published a Nature paper on that. But that was just with one team in one location, launching balloons every hour to get that evidence. So there's evidence there, but it wasn't like, really strong, really conclusive. We went back with a National Science Foundation grant in 2020. We had 4 teams set to be in 4 different locations, but you know what happened in 2020. And so we did end up sending 3 teams, actually, but then there was an atmospheric river, which really messed up with the data, and that's a whole other talk to talk about the atmospheric river. So we won't go into that. But really, to do a good job understanding these gravity waves, we need, many different locations across the path of totality, launching many balloons. So the data I'm going to show you in a minute actually shows from the annular eclipse, a site where we had 4 teams, atmospheric science teams together in one location. But before I show you that data, I wanted to show you a couple more things about the project. There was lots of challenges, definitely, and I'm not going to go into all these because I don't have time. But the project is really very technically challenging and challenging in a lot of other ways. So here's just some quick stats. I'll just highlight that 63% of our more than 850 students were underrepresented in some way, which is one of our big goals, to reach that population. This is the statistic that I want to show. So we asked a question in the surveys ahead of the first eclipse, what the STEM identity of the students was, what the overlap was between themselves and a STEM professional. So you can see on the left-hand side that before the first eclipse, 63% saw almost no or very little overlap between a STEM professional and themselves. But then you flip to after the last eclipse, and 69% saw strong or almost complete overlap between STEM professionals and themselves. So now switching to the annular eclipse data. So this is the data I was telling you about, just to walk you very through quickly. So this is a temperature graph. On the right-hand side, you can see the scale of temperature in degrees Celsius, so that's what the colors mean. On the horizontal axis, we have time. So there was a flight every 15 minutes at this super site location, and then up to 30 kilometers. So on the left-hand side, this is data from our balloons, and on the right-hand side, this is European reanalysis data. So this is like global models put together. And you can see gravity waves here in the stratosphere at the time of the eclipse. The dashed line is sunset from the day before. Then the eclipse is in black here. The dark black line is the eclipse. And so you can see these gravity waves here, and then you can also see them. This is the meridional wind or north-south flowing wind. You can see gravity waves is here as well. So I'm pretty much out of time, into my time for questions, but I just want to show you really quick. This is engineering data, switching to engineering. Here's tracking from the annular eclipse, because these balloons are tracked. This is at the same moment in time from the University of Alabama Huntsville Space Hardware Ballooning Club, looking in all different directions, just giving you a quick peek. But really what you want to do, so this is the complete surround data, completely flattened out. To give you an idea, what you really want to do is look at this, if at all possible, in a VR headset. Watch how the sun winks out as the shadow comes here. But you can also, I'll show you the QR code in a minute. You can look on your computer all around, look on your phone all around. It's just absolutely amazing. So to do that, here's a QR code that brings you to our data results slide. You can see the results, and you can see access those 360 videos to look at them however you want on your phone. If you have an Oculus, even better. Thank you.
Thank you very much. That was great. So we have time for a few questions. If you want to ask a question, please use the microphone in the center of the room there. Well, I have a quick question. Oh, go ahead.
Thank you. You mentioned when the atmospheric river was happening that messes everything up. What other kind of confounding variables do you have to consider even when it's not like such a more extreme weather event?
So yeah, the reason we fly 24 hours before is to get an idea in that particular location of what the weather, is typically like from mountain ranges and all of that kind of thing. So that's why we start flying 24 hours before the eclipse. And then part of the reason we had a super site for the total eclipse as well, but where that was, the weather wasn't great. And so there's some signal there, but it just is not as nice as the super site for the annular eclipse because the weather was amazing there. So you can pull it out, and we have pulled gravity waves out from where the atmospheric river was in Chile in 2020. It's just more complicated.
My question is, do you plan to continue the project by going to, for example, Spain in 2026, or is this it?
So us directly, so we're NASA sponsored through the NASA Science Activation Program, and through NASA it's really very difficult to bring people outside of the country. So not really planning to go to Spain, although we're working with several different groups like in Australia and things like that who want to learn how to do the project on their own in other places.